Hello, everyone, and welcome to our webinar entitled Efficient Generative AI for Images and Videos. With a text prompt and a click of a button, you can generate 2D and 3D images as well as videos. But the question is, at what cost? Machine learning models face challenges such as high computation, large memory costs, and data inefficiency. The Qualcomm AI Research team has tackled these questions. The webinar today is brought to you by Qualcomm and is a continuation of our webinar series on AI. My name is Armina Stepan. I'm with the tech marketing team here at Qualcomm Technologies, and I'll be the moderator today. Before we get started, I'd like to show you how the webinar platform works. At the bottom of your screen, there are multiple application widgets you can use, including a widget to download today's presentation. All the widgets are resizable and movable. The slides will advance automatically throughout the event. At this time, we recommend that you disable your computer's pop-up blockers. This allows the slide to advance throughout the event. You can participate in our Q&A session by asking questions at any time during this webinar. Just type your question into the Q&A widget and then click the submit button. We will answer the questions after the presentation. Also, if you're experiencing any technical problems, please type the issue into the Q&A widget, and we will be glad to help. I would like to now introduce our presenter for today, Amir Hossein Habibian. He is Director of Engineering at Qualcomm Technologies. His work in the development of efficient neural architectures across various domains, including video compression, object detection, semantic segmentation, denoising, and super resolution, has been published at key conferences such as CVPR, ICCV, and ECCV. Amir, please take it away.
Yes. Thanks for the introduction, Armina, and thanks everyone for attending this webinar. I'm very excited to share some of the latest research that we have been doing at Qualcomm with you today. And as we all know, we are facing a wave of generative AI, started with language models, and now getting to another domain, in particular images and videos. And for today, I plan to talk about one of our goals at Qualcomm, which is to bring this new technology to the edge, as we believe decentralization is a crucial step to offer generative AI to billions of users. For today, we have quite a bit to cover, and we will start with some background on generative AI for vision. And then we will deep dive into 4 of our very recent research on efficient generation of images, video, and 3D objects. And we also going to talk about one of the applications of generative AI to create training and test images for automotive that we just shown, I think, earlier this month at CES. And we will finish up with the Q&A. Let's start by recapping what generative AI means and what it can do for us. Basically, these generative models are large machine learning models, usually with billions of parameters that are learned unsupervisedly on a massive amount of data, usually from internet. And these large parameters and large capabilities allows them to generate novel content, such as new sentences, new audio, new images and videos, which they haven't seen before, just emerging behavior by combining all this type of unseen images and interpolating between them into new content. And obviously, these capabilities opens up a whole lot of new applications to generate contents that can be as complex as actually software programs. And in the visual domain, there has been quite a lot of breakthroughs in the past year or two, allowing us to generate completely new images and videos from textual prompts or even visual prompts like sketches, drawings, edges, segmentation maps, where you define some rough, high-level representation of what you want to generate, or giving some example of like a first frame of a video, like an image that you want to build a video on top of that, and the generative model actually can generate a content very accurately in line with what you have asked for, and realistically too. And actually using these powerful generative models, they have been used for providing a lot of advanced image and video editing techniques these days. For example, by editing shapes, appearance, some certain attributes, or even style of the some particular objects, or even the whole scene. Some editing capabilities which hasn't been available before with classical editing tools. And more recently, 3D content generation is getting a lot of promising and exciting research coming out there. And this is a very important task for many robotics and XR applications that you really you need your real application needs 3D assets, and with manual creation of those assets takes actually a lot of time a lot of human time, and being able to generate these contents, with just a single textual description will be very important. And we are seeing some big progress made there by the community. And for those who has attended our previous webinar by my colleague Joseph Soryaga, may remember our demo that was shown in the Snapdragon Summit last year, where we demonstrated fast stable diffusion demo that could generate 512 images with a very high qualities, close to the original stable diffusion in sub 1 seconds on an Android phone. And actually, stable diffusion model has become a new AlexNet for those who remember the image and excitement in the early deep learning era. And actually, this stable diffusion is becoming another backbone for that is being used in a lot of generative vision models, like image models, video generation, editing, 3D models. They mostly build on top of this image stable diffusion model. So I want to emphasize that the efficient support of this backbone has been a key milestone in progression of generative vision models on the edge, and we are very happy and excited about it. And here I want to emphasize, highlight some of the key challenges that exist in developing and deploying large vision models. Not surprisingly, the computation and memory costs are major challenges. And compared to LLMs, LVMs usually have less number of parameters, like 1 or 2 billions, which is less than LLMs, but they deal with much larger and much higher dimensional data, both in terms of their activation function, the output which they have to generate is much, much larger. That makes the computation and memory management very challenging for those type of models. Especially for video, for example, if you want to generate dozens of frames, you need to preserve actually a very, very big tensor that processing it and managing the memory, how to keep it, especially on edge devices, is extremely interesting and challenging. And another challenge, of course, is the data inefficiency, because these models basically requires, if you want to train them from scratch, they need billions of samples, like what we see for image models, like a stable diffusion, which builds on top of Lion 5 billion, and DALI. All of these generative models are trained on billion scales. And for some certain areas, like videos or 3D, or new domains, if you want to go for certain domains, providing these new data like radars or point clouds or all type of new modalities, providing this amount of high quality data is very challenging, which basically encourage the research on how you can do the transfer learning, how you can reuse some of the from adjacent areas, like, for example, for images, how you can extend an image models, image pre-trained models, or image data itself directly to go for these other modalities without the need to collect all this billion scale data set again and again from scratch. And yeah, let's start by getting into the first work that I want to share with you today. It's a fresh research released last month from our lab called Clockwork diffusion for efficient image generation. But before getting to that, let's introduce a couple of key concepts. And starting by diffusion model, that we will hear it a lot during this presentation. And diffusion models are basically a class of generative models that learn to remove a little bit of the noise from their input at every step. And once they are trained, they can generate a whole new content by starting from pure noise and gradually removing the noise in multiple denoising steps till generating a fully cleaned or fully denoised sample. Here on the right, we see a more detailed architecture of the stable diffusion during sampling that starting from a pure Gaussian noise, it runs a denoising model that is actually a unit in most of the state-of-the-art models, either a convolutional or fully transformer-based unit, as we see in like a DIT architectures. And this denoising unit is runs for dozens of steps. That these steps is also determined by a noise scheduling algorithm called the scheduler there. And and actually each of these denoising step is also conditioned by some input prompt, which is encoded by some off-the-shelf text embeddings like Clip, that it introduces some control or some guidance during the generation, so that you just don't randomly generate something, you actually generate something which is conditioned by your input. And as you can guess, this iterative unit is the what is a main bottleneck in diffusion modes. Actually, it used to be a huge bottleneck, and when for early models like the original stable diffusion model, which needs to run this process for 50 or 20 steps, and now thanks to all these, okay, my, sorry, yeah, and thanks to these new scheduling and new distillation methods, now this number of steps has been reduced to up, like 8, 4 even steps, but still, due to a lot of parameters, most of the parameters of the model are still baked into the unit. So it is still the main bottleneck. So optimizing it would highly benefit the image generation and later on other downstream tasks for sure. And the next concept that I want to bring up is model distillation. It's a well-known technique to distill any neural network. Basically can be generative or discriminative, whatever, and into a smaller model called as student, which this student is learned by matching the output of the original teacher model. And after being learned, you can actually at inference, you can just use replace your fat teacher with your small student and get efficiency gains. And inspired by this model distillation, recent works in diffusion models try to learn a student that basically has exactly the same architecture, a number of parameters as the teacher, but try to match multiple denoising steps of his teacher in a single step. And by doing so, you can reduce the number of unit forward passes a lot. That obviously accelerates the sampling process. And yeah, let's have a closer look into the unit, the denoising unit that we briefly discussed. And here we see the details of a multi-resolution unit. And we know unit is a hierarchical representation. It makes multiple resolutions of the input with some additional skip connections from encoder to decoders. And this is basically de facto denoising architecture for diffusion models. And as we see, a unit is made of a low resolution representation, the ones which we see here in black, in green. This low resolution representation usually represents high level structures, such as global scene layouts or object configurations, those type of high-level structure of the image. And a high-resolution representation, which I show here in blue, basically refines these global structures by adding high frequency and local details, such as textures. And so this is basically the intuition behind our work in Clockwork, is that due to their coarse structure, it should be easier to distill low-level representations than the high-resolution unit outputs. So most of the step distillation works try to distill the output of the unit, which is actually can be quite a lot of details and hard to distill. You cannot afford, cutting some parameters. But if you go to the lower and deeper layers of a unit, those layers are actually quite more compressible. That was our intuition, basically. And we verified this intuition by doing a small analysis, as I show here, that basically we introduce the same amount of perturbation, and this perturbation is actually just some noise to simulate the distillation error, because when you distill a teacher into student and a low capacity student, always there is some errors. And here we try to simulate this distillation error as some sort of perturbation mechanism. And by introducing the same amount of perturbation at different resolution of a unit, as we see here on the vertical axis, like a low-level representation, mid, and high, just refer to where we introduce this perturbation at which scale. And actually, we do it at different stage of the generation that you see on the horizontal axis. You can start this perturbation just from the beginning, or after 2 step, 3 step, or actually step 15. And as we see here, a unit naturally very well handles the perturbations on low-level features, whereas the perturbation of high resolution features significantly degrade the generation output. And this motivates us that, especially here, if you look at the first row, basically, if you perturb the noise, from a step 3, 4, actually it doesn't really. And by the way, the bottom right is if there is no perturbation. That's actually the model performance in absence of any type of noise. We see the model generations can be pretty close to this if the noise is injected into the low-level representation of the units. And here we see our Clockwork architecture that at a certain sampling step, which actually is determined by clock rate, a predefined clock rate, we use an efficient student architecture that we call here an adapter to predict the low-level features instead of running the whole low-resolution part of the unit. And we designed this adapter to have a recurrent structure, which is very important, actually, that not only look at the input from the current time step, these blue circles here. So our adapters not only look into these blue circles, but also uses the output from the previous time step, because that might be known. Actually, you might know that how this low-level representation should look like if you have access to previous time steps, these black cycles, dark cycles. And basically, this adapter can be as simple as an identity mapping. So nothing, no parameters, just an identity mapping, which basically makes this RNN like a forward propagator, something that just copy or propagate the features, the low-level features from the previous sampling step. It's like you lock the structure of your generation during the whole process, something like that. Or can be actually better to be a parametric function, which is very thin, shallow, efficient, convolutional networks, just a stack of 2 ResNet blocks, for example. And then that parameters can be learned with some simple distillation framework. And we actually do something more interesting here. I refer to look at the paper, something we call like backward distillation. That's a very interesting way to distill the models. And we applied Clockwork on top of various unit backbones and see consistent flop reductions around 50 to 60% at a comparable or even a better generation quality in terms of FID. And this is also interesting why this is not expected, right? Because this is an approximation, and why it should even increase the FID. It should always just make it worse. But we actually realized that when we were looking at this model, we realized that the shallow path of the representation is responsible to generating details and sharp structures. Even if it is just fake or wrong, if you just run a shallow part of a unit over and over, even if the generation is random, generation is always crisp and sharp random instruction, sharp random actual generations. Whereas the bottom features can be quite blurry. And so basically, I think when we do Clockwork at the same flop rate, this is running the shallow more frequently than its baseline because that's cheap, so it can afford to run it more, which leads to higher details and more sharper images. That's why it's even actually increasing, surprisingly, even increases the quality. And here we are seeing different units. The first row is like a stable diffusion unit, that the typical version 1.5 in this case unit. And if you apply on it, you got like a 48% gain. And this efficient unit is some architectural optimization of unit by removing some of the certain layers like costly attentions in the shallow layer. We still see the same improvement. And distilled efficient unit basically performs both step distillation and even guidance distillation. So it's a highly optimized model. And even on top of that, you still get 62% flop reduction. And we also compare it with state-of-the-art efficient diffusion models. And we observe that Clockwork generates high-quality images faster. For example, at a comparable generation quality to Snap Fusion, Clockwork reduces the flops from 4 to less than 3 teraflops, basically, which is good. And we also integrate Clockwork on top of our highly optimized fast stable diffusion model that was demoed at Snapdragon Summit. And this model has been already passed through a lot of architectural optimizations. And we observe that Clockwork still achieves 48% reduction in unit latency by going from 400 to 270 milliseconds. And that's the cost which we actually tried to optimize. That's the cost you have to pay to generate a latent in a stable diffusion. And an overall reduction of 20% in the overall generation time, including clip, autoencoding, encoding, decoding, everything, every cost altogether on an Android phone, and while actually improving the quality of the generations. And the visuals also confirm it. So these models, Clockwork doesn't degrade the visual quality of the original model qualitatively. And we also tried it on top of image editing task, actually on top of an off-the-shelf method called plug and play, or PNP. Here on the top row, we see the input images with an editing prompt, like, for example, origami of a tiger. And in the middle row, we see the edits output generated by plug and play. And on the bottom, we see the results from Clockwork on top of plug and play, which basically performs faster, like a 25% faster without any performance drop. And the next topic that I want to share today is our recent work on efficient video editing. And video editing is a video-to-video generation task that, given an input video and a text prompt, describing the edit, the model should render a new video. And due to their stochastic nature, applying an image editing diffusion model frame by frame leads to severe inconsistencies, as we see on the right video, and which actually is a major challenge for most of video generation and editing methods. And to improve this temporal consistency, the state of the art relies on temporal self-attention that comes at a high computational cost, especially when the number of frames grow. And here we illustrate how self-attention works, both in case of spatial, like frame by frame, and temporal settings. And as we see in this figure, for a given video with n frames, for example, each frame is embedded into m tokens using query encoding, key encoding, value encoding, like the W's here, which results into for an n frames, basically it results in an m by n token in total for the whole video for each key query value. And when doing the spatial attention, the self-attention is conducted individually per frame. That comes at the cost of m squared for each frame. That should be multiplied by n. So in total, m squared in n. And, and for the temporal self-attention, each token can basically attend to each of the m by n tokens within the video. That results in a higher cost of m squared n squared, which is actually growing quadratically with respect to the number of frames. And in addition to its high computational cost, temporal attention also introduces a big memory overhead, which is needed basically to cache the tokens from the previous frames. If you want to compute this temporal attention, you need to cache all the tokens from the previous frame or from the whole of the video around. That is can be quite expensive if you don't have a lot of memory available. And in this work, which we call it actually object-centric diffusion. That's another CVPR submission, last month. And in this work, we investigate whether we can accelerate video editing by reducing this number of tokens, because it seems to be the key in the performance, this number of tokens. And here is our intuition. So to leverage the whole amount of redundancy that exists in video, we just want to use this whole amount of redundancy to compress these tokens. And more specifically, we merge the over-similar or redundant tokens, both in space, like a spatial and temporal axis. Spatial, I mean like two similar pixels of a sky, which are blue, they're redundant. Or if something doesn't move in time, basically there is a lot of redundancy across temporal axis. And once we find these similarities in tokens, we just combine them, merge them, and treat the merged tokens as a single token. That will reduce both the compute and memory costs a lot. And for further compression, we introduce an object-centric token merging strategy that encourages merging the tokens of background regions to preserve more details on the foreground or edited objects. And as we see in this figure, the object-centric token merging, which is on the bottom row, generates better edits. Like it, for example, for this flamingo, the whole neck is lost in a vanilla token merging, or the color is, actually the shape of the Porsche is quite, messed up in a vanilla token merging. Whereas for object-centric token merging, actually it generates much better edits, and that's because if you look at these dots, that's what we visualize what is going on to debug these two models. We realize that it's because basically the object-centric token merging assigns the unmerged tokens, which are visualized in blue, around the foreground regions which undergo editing operations. Whereas the vanilla token merging may assign these unmerged blue tokens on the background, which is a loss. Actually, you're losing compute. You're just wasting compute around the regions which are not that important for your edit. So they will result in a poor generation. So or object-centric actually quite improves the normal token merging quite significantly. And we apply this object-centric idea and actually or optimization on top of two state-of-the-art video generation frameworks, namely Fate Zero and Control Video. And as reported in this table, we observe like 6 to 10 times speed up at a comparable editing quality, both in terms of clip score and temporal consistency. And here we show the videos and the quality, like qualitative comparisons, that in the top row, you see the input videos and editing prompts, and the output of the Fate Zero in the middle row. And also in the last row, we show Fate Zero results accelerated by our object-centric diffusion, which is 10 times faster and still at a comparable visual quality, I would say. And the next topic that I want to briefly share today is on 3D generation, where we use diffusion models to directly predict a 3D mesh for an object from a text prompt. A very fresh work named as Hexagen 3D. I think we just put it on our archive last week. I'm very excited to share it with you. And but before that, let me summarize that the existing 3D generation works can be roughly divided into two categories. One, optimization-based approaches, or that rely on costly optimizations to fit 3D mesh parameters for each input object. That currently takes more than 20 minutes to generate the mesh for each new object for optimization-based methods. And in contrast, feed-forward approaches directly generate mesh parameters without any test time optimizations, using actually generative model within a few seconds. And currently, the feed-forward methods lag behind the optimization-based ones in terms of mesh qualities. And we believe one main reason for this is actually the lack of large-scale training data, something like Lion 5 billion equivalent for diffusion, for 3D data to be trained. And so in this work, we investigate whether we can use a pre-trained stable diffusion, which is actually intended to generate images. Can we use it to improve the quality of the fast, feed-forward 3D generations? And here is the overall architecture, pipeline that we follow that's adopted from the state-of-the-art 3D generation paper called 3D Gen. And it basically is a latent diffusion model that first learns a variational autoencoder with a three-plane latent structure to reconstruct the meshes. And then, after learning this autoencoder, it learns a latent diffusion model to generate this triplanar latent from the text prompts and to improve the generation qualities. And we aim to leverage a pre-trained stable diffusion model instead of learning from scratch, because the current works they don't have 3D generation. They just train on from scratch because it's too different from images. They don't know how to use an image model. They just started from scratch and learn it on data, which actually seems not enough. So and we actually generate these triplanar latents in two stages. First, we fine-tune a stable diffusion model, and actually image stable diffusion model, to generate some large images that we made by tiling 6 orthogonal views of the object, like top, left, right, front, bottom, all this type of orthogonal views. We just concatenate them, tie them into some big image that we call it as a hexaview image. And then we convert these hexaview images into a triplanar latents by basically splitting these views and aligning them by rotation and flipping. And once they're aligned, we just concatenate them across the channel dimension, and finally passing them to a very small convnet to make these images into a triplanar latent from the autoencoder. And here we compare Hexagen 3D versus the recent optimization-based 3D generations. shown in each row of this figure. Each of them represent one of the SOTA 3D generation methods. And we see that all of these methods, maybe except for text mesh, generates very high quality and detailed 3D meshes, well aligned with the input prompt that you can find in the bottom row. And actually it confirms that Hexagen 3D can generate high quality meshes at a comparable quality with optimization-based models, thanks to using of pre-trained models, pre-trained image models, but at much, much faster, like 7 seconds compared to 22 minutes, which is a big difference. And we believe these basically, even though these image models are trained on 2D and there is not explicitly learned for 3D, but they contain a lot of prior knowledge about how objects looks from different views, from different angles. So it should be easy to just learning how to leverage those implicit 3D information from pre-trained stable diffusion model into this 3D task. And that's actually what we're gaining here. That's our leverage to make these feed-forward models competitive to optimization-based ones. And yeah, let me quickly go over the last paper that I want to share today, and which is actually for improving feed-forward models for novel view synthesis. And as some of you may know, novel view synthesis is a fundamental 3D problem where the goal is to, given an input image, which is taken from a particular camera pose, to render the image from a different target view. And recently, there has been a lot of exciting breakthroughs in using diffusion models for novel view synthesis. And one example is a seminal work of 0123 that you see in the middle that shows that by adding camera poses as an additional conditioning, a pre-trained stable diffusion model can learn to synthesize novel views. And basically what they do is that they start from a pre-trained stable diffusion model, and they fine-tune it on a synthetic data set that includes not huge amount, like not comparable to lion data. So it's multiple views of these objects with the camera pose represented in terms of like a rotation and translation parameters. And so they feed this input image to some visual encoders and also combine it with pose and feed it as a conditioning to a stable diffusion model. The stable diffusion model learns how to render the new view out of the source view. And and obviously this can be very fast as a feed-forward method. It can be as fast as running a 2D stable diffusion model, but currently this model are limited to consuming only one single view. The way which is being designed only handles a single view, even though in many applications there might be more and more views available. And that obviously will improve the accuracy if you can use them, but currently it's not clear how these methods can use it. So in this paper, we explored whether we can improve the generation quality of novel, like a feed-forward novel view synthesized methods using multiple and actually variable number of input views available. And of course, we want to do it efficiently. And here I illustrate our pipeline to support variable length input by the model. We call our model valid as an abbreviation of variable length input and diffusion. And we first tokenize each of the source views. We have a bunch of source views, and each of them is tokenized by passing through a visual embedding. In this case, we use mask autoencoder, which actually works better than the original clip encoder used in literature. And we combine these visual tokens with the camera pose information And then we pass all these tokenized views into a multi-layer Q-former architecture, which you can see in the right side. And this Q-former architecture relies on some learnable tokens as query. These are some variables to be learned. And this learnable queries learns to attend to all the views available, which are fed as key and values. And the nice thing about Qformer is that with the same set of weights, so you only train it once, and with the same set of weights, it can handle any number of inputs, basically, because the way which your embeddings work, the way that the cross attention works, you can just expand, just concatenate more and more inputs, and it means just you can attend to everywhere. You don't need to retrain it. And more importantly, the aggregated tokens will always have the same size, regardless of the number of input. What defines this multi-view tokens, the red here, is actually the dimensionality of the learnable tokens, something which you decide a priori, rather than how many views do you have. And this actually avoids increasing the generation cost if you have more views. So otherwise, if you don't use this kind of fixed length output, if you just like naively concatenating your input tokens, you will end up with larger key and values to be fed into the stable diffusion. And so it increases, quadratically increases the cost of conditioning in the generation. So for us, it's important to keep the dimensionality of the multi-view tokens fixed. And here I show some of the experiments that were conducted on public data, Google scanned object data in this case. And we see, as we see on the right, we are comparing the generations from 0, 1, 2, 3 versus or proposed, like a valid proposed with a single view. And on the right column, we see valid when uses 4 views. And as we see, both 0, 1, 2, 3 and single view valid suffer from some poor generations, like for the shoes and hair dryers. You see some frames, actually for some views, we have a very bad novel view synthesis, which is fixed actually when you use 4 views, as you see in the last column, and which is also reflected in the quantitative comparisons that we did with respect to the papers out. And yeah, another analysis here, we see actually like this toy, like this green toy. The target view is like it's kind of seems to be like a toy lion, and when we see, like when you do one view, there are some of the details of the face of this toy missing, that when you start using more and more views, those missing details are being reconstructed better and sharper. The same for the second row. And as we see on the left, by increasing just the number of views, the generation qualities, both in terms of PSNR and LPEEPs, improves. And the nice thing is that the cost, the overall cost, like at gigaflops here, we are reporting, by increasing the number of views is negligible. It's actually less than 4 or 5% of the overall cost when you double or actually triple the size of your input, conditioning input, basically. And as last part of the webinar today, I want to highlight an interesting application of using generative models to improve the existing graphic-based simulators that are actually quite useful and commonly used for many automotive use cases. We want to show generative models actually can improve these graphic-based simulations. We believe because, of course, they are realistic. They are learned from real data compared to graphic engines, which there is always some domain gap. Learning from real data can fill this gap, and also they are more scalable. For those who has worked with Cognata or other graphic-based simulators, you have to spend a lot of time to craft assets, to design the scenarios, put it in the right place. And whereas, with generative models, potentially, designing a scenario can be as easy as just writing a prompt and just push a button. So there is a great potential, and we are actually, for example, you can use it for creating additional training data, for detecting rare objects like animals, as we actually did. And here we see that by generating extra animal data, you can, adding on top of your images, you can actually get like a 70% increase in your AP, like mean average precision. Or you can actually create more test data for safety critical samples, which are hard to collect, like pedestrian or car crashes, or diversifying your test data. If you want to make sure your model has been tested on a whole range of different scenarios and different cases, you can just use these generative models to generate your training and your test data for your downstream tasks. And this is actually an example of a demo that we just showed, I think, earlier this month at CES, showing our animal data generation pipeline that basically we adopted some, image generation models and personalize it for automotive use cases, and how to do it on when you don't have a lot of data, to personalize it, how to make sure the fidelity of the objects. I mean, you generate tight boxes, correct boxes, and putting animals in the right place. And we actually show it is improving the detector performance by adding it. So it was one thing that we showed as an example of applications. Here's another CS demo again, and the focus is on high fidelity object editing. And the thing is that you want to edit you want to diversify your test set, for example, for less common vehicles like classic cars or whatever, which you don't have many examples. And here the key challenge is how to make sure during these edits you don't accidentally change the geometry, accidentally change the layout, or erase some important objects around your target edit which you don't want to edit, you don't want to remove. So there's all kind of handling occlusion. There's a whole lot of corner cases that you want to make sure that are well handled with your editing methods. And that's I think it's a lot to come in this aspect. And in closing, let's reflect on the things that we have discussed today. We basically, in summary, we basically believe that that generative vision on the edge has a lot of potentials and benefits, and it's a very interesting area of research for I think for a lot of people these days, and also for Qualcomm. And we are actively pushing in this direction, doing research, and we hope to keep updating everyone on research and how we are making progress and affecting ecosystem. And with that, I will stop here, and let's open the floor for questions. And thanks a lot. I hope you like the content. Yeah, thanks. And by the way, these are the channels, you probably know it, to get contact with us. By the way, we have some, let's use the time to mention that we have actually some openings, both for interns and actually looking for senior principal researchers and engineers to join us at Qualcomm AI Research. So if anyone very interested, just feel free to reach out. Thanks.
Thank you very much, Amir. Can you stop sharing the slides? Then we can go back to the camera view.
Yeah, sure. Just a second.
Thank you very much for your presentation. Quite a few questions have already come in, and the Q&A widget is still open if the audience members want to ask anything more. To start off with questions, as my personal curiosity is, how close are we to generating realistic footage and movies with machine learning?
Well, that's a very, very good question. Interesting ones. I think not so far and not so close, I would say. I think there are still a couple of, technical breakthroughs that need to be made, I believe. Even though there are some very, interesting early steps has been taken. Let me give some examples. Basically, the long range dependency. So where currently the field is, struggling is to making seconds level temporal consistencies, making sure you are generating the contents which is consistent and meaningful in 5 seconds, 6 seconds, 10 seconds, visually and appearance wise consistencies. And once it is solved, I think, of course, the next level is how to provide the more semantic consistency, something that you basically your next, 5 seconds and 10 seconds and 15 seconds are also coherent together. And there is a the shot level going beyond frame level, shot level, scenes level. So I think that's actually how to incorporate these dependencies and how to model it. That's quite challenging. And of course, there are some work showing that LLMs, like all these multimodal generative models, can do a lot. Like there are some papers showing on some certain restricted settings, like for toy setups like cartoons, an LLM and multimodal models can actually design quite long storylines, making and videos out of it, but in a real wild video setup, I think that's still a very, very challenge. And of course, audio multimodal models, like how you want to sync audio on top of it, and the compute efficiency, what is in core of our attention, is also substantial here. Because if you want to generate, we're talking about, I don't know, like 100,000 of frames, and if you want to generate and modeling long-term dependency also means keeping, I don't know, like a minutes of video in memory and process it and making some sort of conditioning on top of it. So I think that these are also needs a more efficient architectures than just concatenating the frames and leaving everything to temporal self-attention. I think that's not going to scale. We need a more scalable architectures allowing us to do it. And of course, data. I mean, the training data which are available now are all also limited to 5 seconds, 10 seconds video clips. I think that's but yeah, maybe in a couple of years, who knows?
Yeah. Somewhat related to that, to the question about availability of data, or to your point about availability of data, a question came in, which is quite interesting. How can we evaluate the quality of the generated images using diffusion models, particularly in cases where ground truth or high quality images are unavailable?
Yeah, I think that's a challenge which everyone is facing. Actually, how you can the quality of the generated images. There are two aspects. One is easy aspect, which is basically how well it aligns to actually fidelity, how well it aligns to what it is supposed to generate, like your prompt basically. That's easy. There are multimodal embeddings like Clip. You just match your text into the video, like a visual generated image into the same domain and just take the cosine similarity or whatever similarity in the space. That's easy. But the realism, speaking of realism of the images, I think currently people are just relying on unsupervised metrics like FID or inception score, and they basically just do the distribution matching. They just compare your distribution, a collection of generated examples with a collection of real examples and see how well this distribution matches. And at the same time, I think there are a lot of works going on to basically learning more perceptual metrics. It's a very active area of research, learning perceptual metrics. And this can be even supervised, like people. There are some supervised metrics like LPIPs and whole kind of new models that actually try to learn from human preferences. So you have a human, it provides ground truth, preferences from what he likes and what she doesn't like, and the model on top of it, the model learns to predict the quality of the models. That's an actually active area, and but I think that's a very for video it's become even worse because the temporal consistency is also very hard to measure, and the quality of the video is even worse. But for images, there are some at least widely accepted metrics. But for video, like FVD, KVD, those metrics are really has nothing to do with quality, unfortunately, in my opinion.
See. You presented quite some new methods that the Qualcomm AI Research team has developed. And my question is, can any of these methods be used together? For example, Clockwork and object-centric diffusion?
Yeah, I think most of this has been quite generic methods. I mean, there can be injected, as we also saw in some of the experiments, they can be just injected and integrated into any method. Like in case of Clockwork and object-centric diffusion, sure. I mean, in object-centric diffusion, we have been, I mean, the Clockwork, even though it reduces the backbone cost, but still those high-level features and unclocked units, they still have a lot of tokens, a lot of attention operation is going on, that if you can compress and merge those tokens, you still gain. And actually, this is something which we're doing currently. I mean, combining this object-centric diffusion within a Clockwork backbone to just get better. Yeah, I think that most of them are quite compatible.
Speaking of Clockwork, we've received this question too. If people go to the paper, the paper and archive of Clockwork, is the implementation code also there, or is that not available yet?
The implementation code, if this is in progress, actually, we're gonna share it. Just stay tuned. So this is in the paper. I mean, just submitted. Actually, we just got the reviews yesterday. And we are sharing the code, which would take, I think, a couple of weeks or months. Yeah, it's coming.
That's great to know. Let's see, quite a lot of questions are coming in. All right, I see some questions on the 3D side. So the generative images should be pre-trained models as 3D meshes, right? That's one of the questions.
Yeah. Okay. Yes, I think it's built on top of image models. Yeah.
Yeah, and in Hexagen 3D, can you directly generate the latents without generating the hexa views first?
Yeah, that's a good question. In principle, yes. I think in principle the diffusion model, stable diffusion, can be directly try to predict this triplanar representation, but we observed actually these models are still learned are image generators. So I think it's always better to first, as an intermediate generation step or as a guidance generation, try to generate 2D images with them, like these hexa views, for example. These are 3D concepts, but still in 2D image, just concatenation of a larger tile of images. And in our experiment, we saw that these intermediate, like a guidance steps, helps a lot. Actually, we got, I think, like a 3-4. Let me look up the numbers. Actually, if you don't introduce it, I should have it somewhere. Yeah, it's like 4 clip scores get from 24 to 18. So you lose a lot if you directly try to predict the triplanars. Yeah, so it's essential step.
Right. Another question came in, and that's about video specifically. So has Qualcomm explored LLMs for video enhancement tasks?
I'm not aware of any methods, any current effort on that, but LLMs for video enhancement, that's interesting. I can't connect it right away. Yeah, I actually would love to hear more about what specific angle is this question coming from. I haven't seen that. Not just Qualcomm. I think even outside. I mean, from my knowledge, I don't know if that's something which is being explored. I haven't heard of it.
Yeah, perhaps the person that asked the question can follow up on that. Yeah. As we're approaching the end of this webinar, I have another question to kind of round things off, and that is, what are your future research directions for you and your team?
Yeah. I think we are very well focused now on video generation. I mean, speed up efficiency of video generations. I mean, that's a very active area, and going ultimately we want to run, generate long videos fast on the phone. That's our mission, and we're very excited about it. And also, I mean, trying to use generative models for downstream tasks. We talk about automotive, for example. There are tons of applications there, from, I mean, 3D generations, like a bird eye view generations, lidar, multimodal generations. There's a lot of angles that generative models can expand the scope of these simulators, and so these are actually our current focus that we're very excited about.
All very exciting work, and we're also looking forward to see some demos of the work presented today. Thank you very much, everyone, for attending this webinar. We will try to also reply offline to some of these questions that we didn't manage to get to, yeah, this webinar will be available on demand afterwards. I would like to thank the speaker again and to wish everyone a great rest of your day.
Thanks a lot. Thank you.